welcome to this month's STEMS webinar. So we are very happy to have Raphaël Huser as our speaker today. So Raphaël is an assistant professor of statistics at King Abdullah University of Science and Technology, where he leads the extreme statistics research group. His research mostly focused on spatiotemporal extremes. So he's especially interested in developing statistical methods for the modeling, prediction, and assessment of risk that relates to spatiotemporal extreme values. And he's interested in applications in geosciences and environmental sciences, especially as far as extreme values go. He holds a PhD in statistics from EPFL in Lausanne, Switzerland, which he obtained in 2013. And and today he's going to talk about high-resolution modeling and estimation of extreme Red Sea surface temperature hotspots. So with that, thank you very much, Raphaël, and please go ahead. You can go ahead with the screen sharing.
Okay, thank you very much, Michael, for the introduction. Thank you again for the invitation to you and all the organizers of this very nice series of CMU STEMS webinars. Okay, so I'm gonna share my screen now. I hope you can see it.
Yeah, works fine.
Okay, perfect. All right, so yes, so as Michael mentioned, I will talk about high resolution modeling and estimation of extreme Red Sea surface temperature hotspots. And this is a joint work with Arnab Hazra, who is my postdoc at KAUST. So for those of you who don't know what KAUST is, so KAUST stands for King Abdullah University of Science and Technology. It's a fairly new university founded in 2009 in Saudi Arabia, so 100 kilometers north of Jeddah by the Red Sea. And so here you can see actually the campus. And I'm currently talking from that building here. So this is my group, the Extreme Statistics Research Group. As was mentioned, we are mainly interested in modeling spatial and temporal extremes in different contexts, but mainly applied to environmental applications. And so this work is joined with Arnab, who is standing here on the top left. And the other members are either master student or PhD students in my group. A very brief advertisement. I'm currently looking for 2 postdocs that would work in the following areas. So one would actually work on extreme value theory and statistics, mainly in the context of spatial extremes, with an emphasis on computations. And the other postdoc will work on spatial statistics for point patterns with applications in geomorphology, which is landslide science. And so this will be a very interesting interdisciplinary project between seismologists, geomorphologists, and statisticians. So if you're interested or know somebody who might be interested, please feel free to well, circulate this advertisement or contact me afterwards. Okay, so this is the outline of the technical part of the talk. So I will first start with a brief motivation. Then I will introduce the data set that we analyze in this study. And then I will mention some classical models for modeling spatial extremes and their limitations, because we are interested, as I said, in estimating extreme hotspots. And then I will propose the model that we fit and discuss its properties. I will discuss also Bayesian inference and how we estimate these extreme hotspots. Finally, come back to the application, discuss some results, and conclude with some final remarks. So the paper is here. Has now been accepted at the Annals of Applied Statistics, so it's not yet published, but it's there. It's to appear there, and you can actually find it on arXiv, a preprint on arXiv. All right, so as you might know, the Red Sea is the host of many different kinds of coral species and fish. So here is the Red Sea. It has Saudi Arabia on the east side and Africa on the west. And you can see on this map here, each dot, red dot, represents a coral reef. So you can see that the Red Sea really has a lot of coral reefs, mainly near the coast. But it turns out that about 50% of corals have died over the last 30 years worldwide. You can see here in this picture in the middle, this is a healthy coral. And on the right, this is dead corals. And this is mainly due to the increasing ocean temperature. Of course, there are other factors as well, like salinity, for example. But the increase in ocean temperature is one cause, or the primary cause, of coral bleaching and death. The coral reefs of the Red Sea are less studied than those of the Indian Ocean and the Pacific Ocean. So this was actually the motivation behind this work, the applied motivation to actually be able to model, identify, and predict extreme sea surface temperature data in order to assess the risk of coral bleaching within the Red Sea in future years. Okay, so let me now discuss what kind of data we have at our disposal. So this, the data set that we used comes from the project OSTIA, which stands for the Operational Sea Surface Temperature and Sea Ice Analysis. And it actually uses satellite data as well as in situ measurements from buoys. And it generates daily sea surface temperature estimates free of diurnal variability on a very, very fine grid at a high resolution of 0.05 degrees by 0.05 degrees, which is about every 6 kilometers. So in total, we have about 16,700 grid cells over the Red Sea, which is quite huge. And we have the data from 1985 to 2015, so 31 years, which amounts to 1,600 weeks. So here in this work, actually the data were very complicated, as you will see, very non-stationary. There are many different things that are difficult to model. So here we actually focused more on modeling spatial dependence, the spatial patterns, the spatial hotspots, rather than space-time dependence. And so for this work, we actually thinned the data, keeping only 1 day per week. And then we modeled the data for each day of the week, assuming independence between the replicates. So of course, for coral bleaching, it's also important to know how temperature will actually persist at very high levels. But we kept that for future research. So here you can see actually 3 snapshots of the data at 3 different kind of extreme days. And you can see that there is, of course, a north-south gradient, and the patterns of high temperatures actually vary quite significantly between these different days. So just to explore the data a little bit further, we first, in an exploratory analysis, fitted a simple linear regression model of this form, with T being the index of the year to the quarterly and annual means at each grid cell separately. And here you can see on this map on the left, this is the slope coefficient estimated for each grid cell for the first quarter mean. And in the middle panel here, you see the same thing, so the slope coefficient, but for the third quarter. And on the right, you can see the slope for the annual mean. So what we can see from this graph is that the slopes, or the trends, the time trends, profiles actually vary both spatially as well as seasonally, right? So here you can see already some very kind of tricky non-stationarity to model. So overall, the mean sea surface temperature varies across space, weeks, years, and the effects turn out not to be additive. We also explored how the dependent structure looks like. So what we did in this exploratory analysis is first remove the mean and then looked at the standard deviation of the residuals. So this is plotted on the left here. You can see again very high non-stationarity in these standard deviations. Then we looked at the spatial correlation with respect to the center point in the Red Sea. So here you see that, for example, the correlation between a grid point in the north with respect to the center is about 0.5, but the correlation with respect to a point in the south is about 0. So again, you take 2 points or 2 pairs of points at the same distance, but you get different correlations. So this is an indication again that the correlation structure is also non-stationary. And then actually we are interested ultimately in estimating hotspots, extreme hotspots. And so the tail dependent structure plays a very key role here. And so to explore a little bit the structure that we get in the tail, we looked at this coefficient here, which is also called the tail correlation coefficient. So it is a measure of dependence in the tail. So what we do here is to look at the probability that a grid cell experiences an extreme event. So the Y1, which is the measurement at a certain grid cell exceeds a certain high threshold, given that you have a similar extreme event at another location. Okay, so this is a function of u, which is a quantile on the uniform scale, and then you can consider the limit as u goes to 1. So this chi here is called the tail correlation coefficient, and we get asymptotic dependence when chi is positive, or asymptotic independence when chi is actually equal to 0. So here on this map on the right, you can see the spatial tail dependence coefficient with respect to the center point again. And what you see is that, in fact, this coefficient, which is here estimated at a 99% level, is non-zero over a large portion of the Red Sea. So this indicates that we need a model that can capture asymptotic dependence. So overall, we want a model that has the following features. The mean structure should be non-stationary. The effects of space weak and here are non-additive. And then we are very interested, as I said, in estimating extreme hotspots. So we want to make sure the tail dependent structure is well estimated or is flexible enough. But also we would like to estimate these hotspots by the end of the 21st century. So we need to make projections for the future. And so this means that we cannot just use a linear trend, which would be a bit doubtful. So here we would need to include some kind of trend component that involves somehow climate-based projections based on different greenhouse gas emissions, such as RCP 4.5 or 8.5. As I said, the spatial covariance structure is non-stationary. We have also the non-stationary tail dependent structure. The model, in principle, should be very flexible, and because we have a lot of different kinds of non-stationary behaviors, both in margins and dependence. And so it would be good to have a semi-parametric model. And again, so the spatial dimension is very large, about 16,000 grid cells. So we need to design the model in such a way that we can fit it in reasonable amount of time. And so this means that we need somehow to have a kind of sparse underlying probabilistic structure in order to make these computations fast. And finally, from a Bayesian perspective, we would like to have as many closed form posterior distributions as possible for fast convergence and good mixing. So these are the objectives of that work. Now, as I mentioned, we are interested in estimating extreme hotspots. And so it makes sense to think about the models that have been proposed in extreme value theory or spatial extremes in order to see if any of these models would actually be applicable in our case. But before we talk about extremes, we can also look at the literature, the geostatistics literature, and see what has been proposed. So it turns out that there are many different kind of techniques that have been proposed to handle large data sets in spatial statistics. You can think about, let's say, the Vecchia approximation, low rank approaches, fixed rank rigging, Gaussian Markov random fields, which would induce sparsity in the precision matrix, or covariance tapering, which would induce sparsity in the covariance matrix, the predictive process, and so on and so forth. There are many different kinds of methods. And these are well, let's say, compared and summarized in this paper here, Heaton et al. So you can have a look if you're interested in this. But most of these methods assume that the process at hand is Gaussian, which implies asymptotic extremal independence. And as I mentioned, we would like a model that can capture asymptotic dependence. And also the Gaussian distribution is not flexible enough. It has very light tails and so on. So we cannot just use these techniques for the data that we have. To make the model more flexible, you can think about semi-parametric geostatistics. And some papers have proposed models there. And these are actually more flexible than Gaussian processes. Bayesian computations can be done, let's say in relatively low dimensions typically. But again, if you have a finite mixture of Gaussian processes, this leads to asymptotic extremal independence, and we would like to be able to capture asymptotic dependence. So now turning to spatial extremes, I won't go into the details, but just to give you a rough idea of what has been proposed and has been done, one possibility to model extremes is to use max stable processes. And why are these models useful, or why have they been used? It's because they turn out to be the only possible limits for spatially indexed block maxima. So they have a very appealing asymptotic characterization, right? So if you look at block maxima pointwise of certain processes and you rescale them appropriately, if there is a limit that is non-degenerate, it has to be a max stable process. And max stable theory is well understood. They have a nice spectral representation that can lead to different kinds of max stable models. They can capture asymptotic extremal dependence, which is good for our case. So the chi coefficient that I introduced before is always positive for any pairs of sites. But the issues are that actually in many applications, these models are found to be too rigid in finite samples. This is due to the strong restrictions that is imposed by the max stability property. And also actually the spatial block maxima for which these models are really tailored or designed for may not correspond to real observations, because maxima at different sites may actually occur on different days. So you can think that perhaps so it's a bit strange to fit a model to kind of artificially created spatial block maxima. So you don't really model the spatial extreme events that effectively took place. But from a practical perspective, perhaps the most problematic issue here is about computations. So max stable processes are very intensive to fit in moderate or even very small dimensions. So the reason is that the joint density, which means the likelihood for a single replicate, has this form. And here we can see in the middle here, you have a sum that is indexed over the set PD, where PD is the set of all partitions of 1 up to D, and D is the spatial dimension, so 16,000 in our case. So you see that the total number of partitions is the Bell number, which grows super fast to infinity. And so this is totally out of reach in our case. So other techniques have been proposed, like pairwise likelihood, but then you have issues if you want to use them in a Bayesian context and so on. So what else can be done? More recently, our Pareto processes have been proposed to model extremes defined as threshold exceedances. So there are different ways to define what a threshold exceedance means in the spatial context, right? There is not a unique definition. And that's what we have in R here. So R stands for a risk functional. So you can define spatial exceedances, threshold exceedances, in terms of a risk functional. For example, you can say the spatial average has to be large, or the minimum over the domain has to be large, or the maximum has to be large, right? So this is a very rich framework that leads to interesting models. And it turns out that these R Pareto processes are a bit analogous to max stable processes in the sense that they are also the only possible limits for spatial threshold exceedances. They are meant to model the original spatial extreme events that effectively took place, so that's good. They can also capture asymptotic dependence, so that's good. They have a convenient stochastic representation, and they also have simpler likelihood functions of that form. Now, the thing is, usually we use a censored likelihood because the low values, non-extreme values, they need to be censored to prevent them from influencing the fit of the extremal dependent structure. So that's an issue, because censoring means that you have to compute integrals. And so in practice, these models are still limited to moderate dimensions, about 50 due to this multivariate censoring. There is another practical issue, and this is related to how to choose the threshold view, the threshold that define extreme and non-extreme data, especially in a very non-stationary context like we have here. It's actually not a trivial issue. And this can be very actually tricky to define the threshold to use. So now, what else can be done? So there are some papers that have proposed semi-parametric spatial extremes model. And the idea here is to develop models that have high flexibility both in the bulk and the tails, so that we don't need to actually select a sample of extremes to fit the model, but we can actually fit it to the whole data set from low to high quantiles, with the hope that it would provide a good fit both in the bulk and the tail. And to get a flexible model, typically we can use semi-parametric spatial mixture models. So mixtures, they can probabilistically and automatically cluster observations that are normal or abnormal, or you can think of them as coming from the bulk or from the tail. And this means that we can, in this way, bypass threshold selection. And this is a very nice feature of these models. Again, depending on the mixture components, the spatial mixture can actually capture or may not capture asymptotic extremal dependence. So we have flexibility in this. And Bayesian computations can be quite simple if the model is based on, let's say, Gaussian or student T components. Now, in the papers that have been proposed so far, these semi-parametric spatial extremes models are still limited to relatively low dimensions, and so they cannot be just blindly applied to a data set of the size 16,000. So this was another kind of methodological motivation for this work, to actually develop a semi-parametric mixture model that can be fitted in super high dimensions. All right, so now we will discuss the model. So it's a semi-parametric mixture model. And what we do is to model the sea surface temperature data in this way. So we assume that we can decompose it into a mean component and a residual term here, epsilon. We observe the data over 1,600 weeks, and we treat them as independent, as I mentioned. Now we further...
there's a comment, so maybe we can actually, if we talk about the model, we can discuss this comment briefly. So in the chat box, we have a comment from Michael Stein, and I think this is actually in reference to in the first part of the talk, you showed this plot of the empirical chi values, and Michael is commenting that that given that plot, he's not sure if that means that you need a model for the asymptotic dependence of the extreme, and he says that it all depends on how you take limits. So would you like to comment on what that plot implies in terms of whether you need
okay, so yes, I agree with that comment. So here we actually looked at the chi coefficient at the level 0.99, so the 99% quantile. So if we want to assess whether we need an asymptotically dependent or independent model, we would need to actually look at a sequence of quantiles and to see how this converges. And in practice, it's always difficult, in fact, to know what is the limit as u goes to 1. So in practice, we can never really know if it's asymptotically dependent or independent. But what we observed, at least at this level and at other lower levels, we looked also at the 95th percentile and all levels in between, is that the tail coefficient was fairly high over a large portion of the Red Sea, and the way this coefficient behaved as a function of u was actually fairly stable. So this gives us an indication that perhaps the limit is positive. Another way to look at it is extremal dependence somehow gives you an upper bound to the risk, right? So if you want to be, let's say, if you're not sure and you want to be on the conservative side, perhaps it's better to use an asymptotically dependent model. But I agree, we cannot be 100% sure that the data are asymptotically independent. But another thing to keep in mind is we deal here with sea surface temperature, And so this is a very smooth and very long range process. And so I think it's fairly natural to assume asymptotic dependence in this case.
Cool. Thank you very much.
Okay, so let me continue. We can discuss it further at the end if something was not clear. Okay, so we further model the mean in this way. So in terms of T1 and T2, so T1 is the index of year, T2 is the index of week. And then we assume that we have a linear model of this form where x T1 to 0 here actually denotes the trend term, but we don't take it to be year or time. We take it to be the rescaled annual mean sea surface temperature projection based on the climate model that uses either RCP 4.5 or 8.5 scenarios. So two different kinds of greenhouse gas emissions. So 4.5 is typically thought of as business as usual, whereas 8.5 is a more pessimistic scenario. And we tried both in our case. And then, so the regression coefficients depend on both T2, so the week, and S space. And we further model these coefficients using splines. So we use here 12 splines across month, so one per month. And we use 189 splines across space to be able to capture the spatial variation of these coefficients. And thanks to these assumptions, we can actually describe the mean vector in this way, and where these times here represent Kronecker products, and this will be actually very useful for computations. Then the residual part, we assume that it comes from a Dirichlet process mixture. So here it's a mixture of densities where these FT terms are multivariate T densities. So with degrees of freedom A, zero mean or zero mean, and the dispersion matrix is in this form. So here what you can see is we have a nugget effect, which is tau squared, and we have this structure here for this covariance matrix here. So H phi H prime, and the idea here is to use basis functions, certain type of basis functions in H, and phi will be a diagonal matrix of weights. So how do we choose these basis functions? We actually decided to use empirical orthogonal functions. Empirical orthogonal functions, or EOFs. So how do we get them? Well, in a preliminary step, we estimated the mean empirically based on the data using least square estimates. Then we actually subtracted the mean. We got the residuals. We then computed the spatial covariance matrix, the sample spatial covariance matrix, sigma hat. And then we did an eigen decomposition of sigma hat, and then kept only the L eigenvalues, lambda 1 up to lambda L, that the largest eigenvalues, and the corresponding eigenvectors H1 up to HL. And then we form this matrix H by just putting these eigenvectors for the L largest eigenvalues as the vectors, as the columns of this matrix H. Okay. So now we have 16,000 grid cells, but of course we keep only a fairly small number of eigenvectors. So this will make this this matrix A, H, phi, H prime low rank, and this is actually very useful for computations. So we can approximate the sample covariance matrix in this form, right? And here you see that we have delta, while in the previous slide I had a phi matrix instead. And so the reason here is that we don't want to use this delta matrix exactly, but we want to put a prior on this diagonal matrix of weights that will be centered at delta. So overall, the covariance matrix has this form because of the mixture. And here in this slide, I show you the first most important EOFs for that were computed based on the red sea data. So the first one is kind of constant. The second one captures the north-south gradient. The third one captures the contrast between the center and the ends of the Red Sea. Then the fifth one, for example, captures the contrast between the southeast and southwest of the Red Sea. So you see that these EOFs have very nice geographical interpretations, and we think they are actually very natural to use here in our case. So overall, the model looks like this, and we call it LTP-DPM for Dirichlet process mixture of low-rank T process. So essentially, different weeks will be grouped into different clusters that will have different spatial characteristics. Now, given a cluster index, let's say GT is equal to K, we can represent the process hierarchically in this form. So, so essentially, it describes a hierarchical stochastic representation of a T process, right? So we have a mean term here, and we have a scaled Gaussian term here on the right, where sigma, the random scale, has an inverse gamma distribution, and then ZT here is a multivariate normal vector, and eta t is the negative effect. So it's IID normal with some variance tau squared. Then we actually put a prior, as I mentioned, on the phi, this diagonal matrix of weights. And the prior that we took was an inverse Wishart prior with these parameters, so that the expected value of this matrix will be exactly delta, the matrix of eigenvalues that we computed from the sample spatial covariance matrix. So this means that actually the covariance structure of epsilon is approximately equal to sigma hat, or at least it's centered at sigma hat. And we put a stick breaking prior on these probabilities pi k. All right, so we can derive the model properties fairly easily. So the bulk and the tail, or the bulk properties of this model is similar to Dirichlet process mixture models. So we have a non-stationary mean in this form. We have a non-stationary covariance structure here. So the non-stationarity in the mean is mainly driven by these covariates here, while the and the splines, while the non-stationary structure in the covariance matrix is mainly driven by these basis functions, these EOFs. Now, regarding the tail dependent structure, we actually get asymptotic extremal dependence, and we can compute this chi coefficient, which is represented in this form. So we can actually calculate it in explicit form. So this FT here is the CDF of the student T distribution. And here M refers to AM is the minimum degrees of freedom among the capital K mixture components. Okay. And R is the correlation structure of the corresponding process. So we get asymptotic dependence unless all these degrees of freedom go to infinity, and instead of having student T processes, we have Gaussian processes as mixture components. All right, let me now explain how we make inference, Bayesian inference, and how we estimate these extreme hotspots. So, so here, what we do is to exploit the separable structure of the design matrices. You remember this vector of means could be expressed in terms of Kronecker products. So we exploit this separable structure to update the regression parameters very fast. So we have a lot of regression parameters, right? So the number of splines in time was 12, and the number of splines in space was 189. So we have about 2,000 regression parameters to estimate, which is a lot, but we can do that pretty fast thanks to this separable structure. And then in practice, what we do is to fix the number of mixture components K within the MCMC, as well as the number of basis functions L. And then we choose K and L by cross-validation. So all the parameters have conjugate priors, which is very nice, except the degrees of freedom parameters, AK. But for them, we actually assign a discrete uniform prior from 2.1, which ensures finite variance, up to 40 on a very fine grid, which means that we are close to a Gaussian process here. And then because we have a discrete uniform prior, we can then sample straightforwardly. So we do 60,000 MCMC iterations. This takes about 10 hours, which is approximately 2 times the time it takes for fitting a low-rank Gaussian process. So we think that the coding is quite efficient for the most complex model. Now, to estimate hotspots, which is the ultimate goal for the reason we developed this model, what we do is to actually follow the approach proposed by French and Sain in that paper, and we extend it to the context of our Dirichlet process mixture model. So the approach that was proposed by French and Sain was actually developed specifically for Gaussian processes, but here we extend it for our model. So, okay, so what we want is to estimate an exceedance region. So we define an exceedance region in this form. So it's the collection of sites within the domain such that the process at a given time point t0 exceeds a threshold u at those locations jointly. Now, this set is a random set. So we don't actually want to estimate this set in itself, but what we want is to find a confidence region d0 u plus that contains the exceedance region with some predefined probability. So that's the goal. Now, how do we do that? Well, what we will do is to first design a test to test whether yt0 Sn is equal to u versus it is less than u. And we do this test for all the points within the domain on the basis of some test statistic. And of course, we have to define what kind of test statistic we will use, and we have to define also what kind of critical value we will use, right? And then we will collect all the sites where we fail to reject the null hypothesis. And so this will give us the estimated hotspot. Now, what kind of test statistic we use? Well, an obvious choice is to exploit y hat, which is a predictor of yt0 Sn. And for that, we will actually use the posterior predictive distribution. Now, why do we need to adjust the critical value? Because we want to achieve an overall family-wise error rate of alpha while accounting for spatial dependence. Okay, so the model is very complex, and so it's not easy to do this exactly. So here we actually rely on posterior predictive sampling. So it works as follows. We will first generate 10,000 samples from the posterior predictive distribution for time point t0 for the whole red sea, the whole domain. And then, so based on the Bayesian CLT, the posterior average will be asymptotically normal, right? With this mean and a certain variance. And so what we will consider for the test statistic is a rescaled version of this posterior average, right? So y hat minus u divided by this standard deviation. And so this will be normally distributed with mean 0 and variance 1 under the null hypothesis. And then we actually need to choose the critical value C alpha in this way. So maybe it's not very obvious here, but we can actually show, we showed in the paper that this is how we need to choose the critical value to achieve an overall family-wise error rate of alpha. And so here the issue is, so you see this minimum is taken over the exceedance region E that we ignore, that we don't know. And even if we know it, we would not know actually the distribution of this minimum. So what we do here is to rely again on posterior samples, posterior predictive samples. So for each of them, for each B, we actually identify this exceedance region, EUB, and then we can calculate the minimum. And then we have actually capital B minima, and based on this minima, we can actually estimate C alpha as the sample alpha quantile based on these samples. Okay, and finally, once we have C alpha, we estimate, or we define the estimated hotspot as the collection of sites such that the test statistic is bigger than this value here. So this is how we estimate hotspots. All right, so let me now come back to the application and I will show you some results. But first of all, so these are the two different scenarios that we use in terms of the time trend. So we considered projections, SST projections for this century, for the end of this century, based either on RCP 4.5 or 8.5. You can see here the trajectories. So the blue line is this RCP 4.5, which is business as usual, while the red line is more pessimistic, and this is RCP 8.5. So most of the results will be that I will show will be based on 8.5. But in the paper, we have both of them. Okay, so to fit the model, first we need to choose the number of mixture components, K, and we need to choose L, which is the number of basis functions to use. And to choose these values, we actually did a cross-validation study. So we took a training set from 1985 to 2010. So this is 26 years. And the test set was 2011 to 2015, so 5 years. And here we actually compared different models. So we compared a low-rank Gaussian process, where K, the number of mixture component, was just 1, and all the degrees of freedom were set to, the degrees of freedom was set to infinity. We also considered a low-rank T process with K equal 1, Dirichlet process mixture of low-rank Gaussian processes with all the degrees of freedom set to infinity, and our proposed model based on mixtures of low-rank T processes. We considered for that model 2 values of K, so either 5 or 10, and 2 values for L, the number of basis functions, either L1 or L2. I don't recall exactly what L1 and L2 were. Maybe it's like something like 15 and 20, like around that number. But L1 was chosen to keep 99% of the variability, and L2 was chosen to keep 99.5% of the variability. So L2 was bigger than L1. And then, so here what you can see is the predictive performance of the model with respect to the low-rank Gaussian process. And to assess this, we actually use the Breyer skill score on the top row here, which depends on a certain quantile. So we fit this as a function of the quantile that we choose. Remember that we want to estimate extreme hotspots, so that's why we actually consider high quantiles here. And on the bottom line, this is the threshold weighted CRPS skill score with respect again to the low-rank Gaussian process. So all these values you see are positive, which means that all the models improve over the low-rank Gaussian process. But overall, if you compare these plots, you see that the blue line for K equal 10 and L equal to L1 is the highest one in most cases. So what is this model? This is actually the low-rank T process mixture, the one that we propose, with K equal 10, so 10 mixture components, and L1s, which is the smallest number of basis functions. So that's the one we use for making inference. Now, this is, I think, an interesting plot here. What we plot here is the posterior densities of the 10 ordered stick breaking probabilities. So we have 10 mixture components, so 10 plots. And we plot them for the Gaussian process mixture in red and the T process mixture in blue. And what you can see is that for the T process, the pi1 here takes care of about 95 or let's say 90% of the data of the weeks. So this means that this T process mixture can somehow distinguish observations that are normal and those that are abnormal. So data that come from the bulk and data that come from the tail. While the Gaussian process mixture, all of these probabilities are fairly high, actually. So it is unable to really distinguish the tail from the bulk. And we think this is an advantage of using a T process mixture. Okay, so these plots now show you the estimated decadal rate of change as estimated by our model for week 7 and week 34. And here the overall sea surface temperature. So you see that there are actually very strong variations as a function of the season and as a function of space. This plot shows you the return levels. So what is a return level? A return level is a value that is expected to be exceeded once on average over a certain period of time. And so here I'm showing you the 10-year return level, the 20-year return level, and the 50-year return level for week 34 and 40, which are two of the hottest weeks for the Red Sea. So either in the so the week 34 is the hottest week in terms of the average sea surface temperature, and week 40 is the hottest week for the south of the Red Sea, if I'm correct. So again, the notion of of return level is a bit tricky to define in a non-stationary context. So here we can discuss that later if you want to know more what we actually calculated. But the bottom line is you can actually calculate these things based on the fitted model. And then what we looked at as well is different kinds of marginal and joint exceedance probabilities, because we are interested in spatial extremes and hotspots. So here what we did was to compute these two types of probabilities. So the first one is the probability that you get at least one exceedance of the threshold U over a certain domain D0, at least one. The second one is that all of the grid cells within the domain D0 exceed the threshold U simultaneously. And so these first type of probabilities correspond to fixing the threshold to a given high temperature value U. Okay, so this gives you an idea of joint exceedance probabilities on the scale of temperatures, of sea temperatures. But looking a bit at the coral bleaching literature, there is a theory that actually corals are slightly adaptive to their environment. And so the bleaching threshold for the north of the Red Sea will be different from the bleaching threshold in the south of the Red Sea. So we also looked at the same type of probabilities, joint exceedance probabilities, for spatially varying threshold that would be defined in terms of a probability P. And so to look at these probabilities, we consider 3 regions. So this region in yellow here is close to Thuel, close to Kaust, where there are a lot of corals. And then here in green, this is the Farazan Islands of Saudi Arabia with a lot of corals as well. And the other one, the purple one here, is the Dahlak Island of Eritrea, with also a lot of corals there. And these are the estimated probabilities based on the models. So this is for week 40, a hot week, and the year 2099, based on RCP 8.5. And what you can see here is, well, first of all, the green lines correspond to the joint exceedance probabilities. The first type, where at least one of them exceed the threshold U, whereas the blue line here represents the other type, where all of them exceed the threshold U for different sizes of domain, depending on different radiuses, right, from the target location. And the black line here is the marginal exceedance probability. So the first row is for fixed threshold, and the second row is for this spatially adaptive threshold, which is more in line with coral bleaching theory. And what you can see is that in these 3 different regions here, the probabilities are pretty high, especially for the Dahlak Islands and the Farazan Islands, which are in the south of the Red Sea. And so this indicates that there might be a pretty high risk of coral bleaching by the end of the century, or at least a high risk of a joint spatial extreme event in these regions. Now, we also estimated the hotspots based on the method that I proposed, that I described for week 34 and 40. for 3 different fixed thresholds, so 33 degrees, 33.5 degrees, and 34 degrees. And you can see that at least week 40 here, these hotspots cover a very big region in the south of the Red Sea, and especially when the threshold is lower, but even at 34 degrees, you can see that the region, the hotspot actually covers or spans a quite wide wide region here in the south of the Red Sea, and it covers, in fact, these 2 islands, the Farazan Islands and the Dahlak Islands. We can repeat this based on RCP 4.5, so this is what we get. Of course, these probabilities are lower, as expected, and we can compute the estimated hotspots. Again, this is what we get. So again, the hotspots are smaller, but nevertheless, you see that at the level 33.5 degrees, we still have actually quite a wide region that is covered here by these hotspots. Okay, so let me now conclude. So we have proposed a low-rank semi-parametric Bayesian model for large spatial data with an emphasis on having a flexible tail structure and where independent replications are available. The model has a non-stationary mean and covariance structure. It can capture asymptotic extremal dependence because we have student T processes as mixture components. And we can make inference fairly efficiently using a KEEP sampler. And we can also estimate spatial hotspots using posterior predictive samples. Our results suggest that large areas of the Red Sea that include major coral reefs are likely to experience very extreme sea surface temperatures simultaneously around the end of the century. And this may have dramatic consequences in terms of coral bleaching and mortality if mitigation measures are not implemented. But in future research, it would be interesting to generalize our approach to estimate also space-time dependence and assess whether spatial hotspots tend to persist over consecutive days, which is actually a key factor as well in this phenomenon of coral bleaching. So this is actually fairly difficult. We actually tried it, but it was very demanding. And for our data set, in fact, the spatial correlation was not the same across grid cells. So you have a spatially varying temporal correlation, and this is very difficult to model. So we kept this as a future research project, but of course, it's a very important point. So that's it. Again, this is the paper. If you're interested, it will appear in the Annals of Applied Statistics. And this is the archive link if you're interested to see a preprint. Thank you very much for your attention.
Cool. Thank you very much, Raphaël. So let me see here if we have any questions. I see some clapping there, which is great. So if anybody has any questions, feel free to, you can use the raise hand button, which I believe this is under the reactions button in Zoom, I believe. So you can use that. You can just put it on the chat box as well if you have any questions. Okay, so I think Michael has some questions. So Michael, please go ahead.
Question, but of course I have questions. So it's very interesting. It's a tough problem and you're taking it seriously, so I like that. You had this kind of Bayesian motivation, but then you seem to be trying to say it had coverage, frequentist coverage characteristics. Do you actually have a theoretical argument for that, or is that just some kind of vague heuristic that you're hoping it will work?
Sorry, I'm not sure to understand which part are you talking?
So you gave these confidence sets. You said you seem to be talking in a frequentist point of view when you were talking about your sets that would include, maybe that was just a matter of language.
Is it for a hotspot estimation?
Yeah, you seem to be talking about this hotspot estimation, right, you know, in a kind of frequentist language. Is that just a difference in languages and you didn't mean it as frequentist, or do you really hope that you have some kind of confidence set as opposed to some vague Bayesian credible set?
Yeah, that's a good question. Actually, we were also at the beginning, we were also a little bit confused ourselves. Well, I'm not sure I have a good answer to this, but essentially we view, I mean, we want to find a confidence region that contains the true value, I mean, the true set with some predefined probability. And so, so it is kind of natural to start by thinking, okay, instead of trying to find the whole region, I will just do it side by side. So I want to actually see if at a particular point in space and time, if this will exceed a threshold U. So in this sense, you can view it as a kind of testing problem, right? You can think of it as a testing problem. And now, of course, you don't want it to be, I mean, you don't want the set to be only about the marginal event. So then you need to kind of adjust the critical value of the test so that it contain, I mean, the whole exceedance region with the probability that you like. But so this is why we actually now introduce these tests. But I agree. I mean, there is we have a Bayesian model, and the language is a bit more frequentist. So, but yeah, I don't really have a very good answer to this.
I guess I was also a bit confused on the same point, because it sounded to me that you calibrate the test based on the posterior. So wouldn't that mean that it effectively has a Bayesian interpretation, because everything's kind of conditional on the data and done using the posterior? Or did I understand that wrong?
Can you show the next slide? I think it's in the next slide where you define 28.
Here?
Yeah, it almost looks like what we're doing for estimating frequentist confidence sets, except that your first slide, you draw posterior samples. Otherwise, it looks very similar to what we're doing.
Right.
We're getting.
Yes, that's true.
But a posterior sample is very different
Yes.
than a sample from the distribution with fixed but unknown parameters. So, you know, I mean, why not have the courage of your convictions and say that these are in some sense credible sets?
Right.
Because then it seems to me the problem is operationally easier, right? You just look at your simulations and you look at what fraction from the posterior, and you look at what fraction of them have whatever property you want them to have. I mean, maybe you're worried that that's taking your Bayesian model too seriously, and you're hoping this will somehow produce more conservative inferences, but then you need to have some argument for why that's the case. Or it would be helpful. You don't need, look, you can do whatever you want, but it seems to me this is, you know, maybe it works, but I don't know why anybody should be convinced it works.
Yeah, I'm afraid I don't have a very good answer. I need to think again about this.
Can you say more about the first line? How you draw the posterior samples? I mean, can you remind us?
Oh, sorry. So these are just from the posterior predictive distribution.
Right.
So, so this is, I don't know. I'm not sure to get your point. I mean, this is.
Can you show the model
just
again?
MC, right? Like,
yes.
You just do MC,
okay.
right?
Right. So yeah, so the uncertainty in model parameters is also taken into account here. If you want all the, yeah.
So I'm wondering, I mean, since your problem is hard, let me try to make it even harder, because we're trying to work on real physical problems. Let's think about what the real problem is here. So as far as I can tell, you are ignoring the fact that you don't necessarily know the relationship between an emission scenario and sea surface temperature. You're just getting that in the future from a climate model,
Correct.
which has its own errors. And then you're also doing an extrapolation from global sea surface temperature to what happens in the Red Sea. You're assuming that whatever relationship you see in the present, that will also extend out into the future. So those are two further deep sources of uncertainty. And I'm wondering, you know, I mean, part of I don't think one wants to take the posterior probabilities one gets out of these kinds of analysis when you're trying to say something about what's going to happen in 2099 too seriously. What you want to be able to say is, look, as far as we could tell, this could happen, right?
Right.
You
Exactly.
know, maybe it's ludicrously too optimistic or ludicrously too pessimistic, but given our present knowledge and our uncertainties about all these things, we can't exclude this possibility. And that seems like a useful exercise to do, and that the kind of analysis you're doing is helpful for. But then why not really say, well, okay, there's all these other sources of uncertainty, and that could make our uncertainty about this problem even that much bigger. And you know, I mean, the scientists are always going to push back against that because they don't want to be told that there's almost infinite uncertainty about these things. But if that's the truth, then that's the right thing to do, whether it makes you popular or not.
Right. I don't know if we can really believe this will be the truth, as you said. I mean, there's a lot of uncertainty about how these things will.
Well, let's even condition on the emission scenario. I
Right.
mean, let's not try to predict how emissions are going to be. Even conditional on the emission scenario, there's a lot of uncertainty in these relationships to sea surface temperature, and then further uncertainty about what this says about local temperatures in the Red Sea.
Yeah.
Is this graph local to Red Sea, or is this some kind of a global graph?
Yeah, it's for the Red Sea. So we, I think there were like maybe 30 grid cells over the Red Sea, and we just averaged them and averaged, I mean, we have one value per year here. Right. So it's
This is based on one model. I mean, you could look at
one model
across models as a crude way of getting at that uncertainty.
Right. But yeah, the thing I'm not sure about is, okay, if you get different models, how would you include or account for that uncertainty in the model?
Well, I would just so I think Bayesians don't have to always integrate out all uncertainties. They can give conditional uncertainties.
Right.
You can say, if we accept this model as producing the correct relationship, here's what we get. And if we accept this model, and just look at how those vary without trying to integrate over them, because that's another hopelessly difficult problem. But it still gives you some senses. Look, unless you know that this model is giving a better sea surface temperature than that model, these are all plausible possibilities as far as we can tell. And that seems to me a useful thing to say.
Yes.
That might be pretty easy for you to do given all the work you've already done. Right? You just have to get your computer to work harder.
Yeah, thanks. Yeah, to be honest, I'm not sure if the model that we used was the best one or whatever for the Red Sea. I think Arnab, when he looked at that, he actually tried to see and to read the papers to see which one was the best for predicting in the Red Sea. So I think I'm pretty confident that we did a good, reasonable choice, let's say. But I see this more like as a scenario type of thing. Okay, so if this is the increase in sea surface temperature for the Red Sea, these are the hotspots that we would get, right? So it's more like scenario based somehow. Yeah, and here we have two scenarios, one that is pessimistic, the other one that is a bit less pessimistic. And we can deduce the kind of hotspots we get in each case.
Cool.
I mean, it's actually, those pictures are a little bit interesting because the RCP 8.5, if you look at global atmospheric temperatures, the trend will be very nonlinear, right? That it starts really accelerating and taking off, whereas this looks fairly linear, and maybe that's right. You know, that makes sense for the Red Sea, but you know, I can imagine scenarios that look much worse than this.
Yes, and actually, first what we did was to have a linear trend, like just year, and then we changed to actually taking this, and actually the model fit. I mean, the results that we got were pretty similar. I mean, with 8.5 was pretty similar to this linear trend. So yes, indeed, it's. I mean, you can see it here on this graph. It's quite linear, and that's specifically for the Red Sea again. Yeah.
Mm-hmm.